Hi everybody, today we're talking about applications of exponential functions. So we've learned what an exponential function is, and now we'll learn what kind of real life things can be modeled by that. So there are many real world applications representing exponential growth. In each case, a variable either increases, so that's exponential growth, or decreases, which would be exponential decay, by a percentage. So instead of going up by 2 every time, for instance, it would be multiplied by 2 every time. Or instead of going down by 5, it might be decreasing by 50% or half. Okay, so some common examples include population growth, bacterial growth, interest rate, radioactive decay, leaking tire pressure, percentage of drugs left in your system. Anything that's being multiplied or divided by a constant amount will be exponential growth. So the exponential function f at x equals a times b to the x in its graph can be used to model and solve these problems. So each of those letters or variables has a specific role to play. So f at x is the target or the final value, okay, so what you're trying to get to. A is the initial value. So let's say a population is currently 3,000 people and then raising by 8% every year. A would be the 3,000, what you're starting at. B is the growth or the decay. So it's either going to be 1 plus a percent or 1 minus a percent. So for instance, if you have 1.15 as your B value, this would be a growth of 15%. If you have 0.85, that would be a decay of 15%, because that's 1 minus 15% to get to 0.85. So anything greater than 1 is growth. Okay, and anything between 0 and 1 is decay. X is the time period. So let's summarize this. Okay, so f at x is the target. A is the initial value. B is either 1 plus r for growth, or 1 minus r for decay. And you can add here that r is the rate, which is in percents, of growth or decay. Okay, and finally x is the number of time periods. Okay, and that's how you break that up. So there you go. That's the general form. So make sure you have that down. Pause the video if you need to. All right, so just a few more points, and that is the basics of what's going on here. So again, I know I keep repeating this growth and decay stuff, but it's probably honestly the most difficult part, so I'm just reinforcing it. So if the problem represents growth, B equals 1 plus R, so 8% growth, the B value would be 1.08. If the problem represents decay, B would be 1 minus R, so 8% decay would give a B value of 0.92, because that's 1 minus 0.08. If it's talking about half-life, your B value is a half, because that's 1 minus 50%, okay? So you're halving it every time. Doubling, B is 2. So it's being multiplied by 2 every time, or you can think about that as meaning it's increasing by 100% every time. So 1 plus 100% is 1. And then just be careful that the units for the growth or decay rate, so the R, have to be the same as the units for the number of time periods. So if I'm saying it doubles every 3 minutes, then your time period has to be in minutes. Okay, if I'm saying that it doubles every hour, then your time period has to be a number of hours. So just be careful that the units match up. Okay, so this is just your basic note of how to look at any exponential function and use it within a realistic situation and interpret the numbers within a situation. Or you can take a look at a situation and now interpret that by modeling it with an equation. So you can go both ways. Okay, so thanks for watching, and I hope you learned lots.